All right, so in each of these examples, we're going to do some modeling of real-world situations. And so for each, we're going to be asked to create an equation or a function to describe a real-world relationship, and we may be asked to use it to answer some questions about that real-world situation. Always in these kind of problems, we've got to be really, really clear and specific about our independent and dependent variables. What are they? And for the three on this page, we're going to actually give the domain and range as well. So, number 22, when we move apartments, we need to hire movers, unless you want to carry all that stuff yourself. And the cost of these fake movers is $100 upfront deposit plus $120 for every hour it takes them to move your stuff. So I think in this case, our independent variable is going to be the number of hours that they work. And what depends on that? I think the dependent variable will be how much it costs. How much it costs to move depends on how long they work for. And in this case, let's use some unoriginal variables x and y. Now, you're welcome to make a table of values here and find an equation from that, but perhaps you remember using your intuition how to create this equation just kind of right off the bat. I think that the cost is going to start at $100, and it increases by $120 every time they work another hour. So our relationship can be described with the equation y equals 100, the flat deposit rate, plus $120 times however many hours they work. So there you go. And our domain and range in this case, well, note to self, if we were to graph this relationship, it'd probably look kind of like this. It'd be a discrete graph. You know, here are your hours, and here's the cost. And so since it's a discrete graph, the domain and the range are going to be just kind of lists of numbers. So for instance, our domain will be 0, 1, 2, 3, and at this point I can say it continues on. And our range, well, it starts at $100, then 220, 340. We just keep on adding 120 again and again and again, and that continues on forever as well. So that's the first problem. All right. Maybe we're getting the hang of this. How about number 23? On February 10th, your car had exactly 30,000 miles on it. And since then, we put on 3,000 miles every month. All right, first, let's define our variables. Our independent variable, we're going to be real clear here and specific, I think will be the number of months since February 10th. And I think our dependent variable will be the number of miles on our car. Now, you know, we can leave it as such, but you know what I'm going to do? I'm going to do this in thousands. So instead of having to write 1,000 again and again and again, we can just write, for instance, 30 to represent 30,000 miles, and 3 to represent 3,000 miles. And let's call this months, we'll call this N, and miles, we'll call this D. I'm just picking random numbers here, letters. So in this case, well, most of these modeling equations are going to look like dependent variable equals. So I think our equation will be D equals, well, we start with 30,000 miles on the car, and that increases by 3,000 miles every time we go another month. So our equation in this case will be 30, or rather D equals 30 plus 3 times N. And the domain and range here, you know, it's really up for debate whether or not, if we were to graph this, the question is whether this graph would look like a discrete graph full of points, or whether, because distance is a continuous kind of measure, whether it be a continuous graph. So I'm just going to pretend that this one is a continuous graph, or we're going to just choose to make this a continuous graph. And so in this case, I would say that our domain would be all numbers greater than or equal to 0. And our range would be all number of miles greater than or equal to 30,000. So I'm going to say that that's D is greater than or equal to 30. Of course, that 30 means 30,000 miles. All right, one more. At 7 a.m., a group of hikers climbing a mountain were at an elevation of 2,000 feet. They ascended at a rate of 350 feet per hour. All right, let's define our variables. Our independent variable, let's make that number of hours since 7 a.m. And our dependent variable, let's call that the elevation of the hikers. And Good to be specific. Let's say in feet. All right, they're doing this in feet, right? 2,000 feet? 2,000 feet. Okay, good. All right, the independent variable, let's give that the variable name n. And elevation, we'll make that h. I'm going to do capital H so we don't mistake it for that n. All right. So I think that, once again, it's going to probably be dependent variable equals, well, they start at an elevation of 2,000 feet, and they ascend, which means they go up at a rate of 350 feet every passing hour. And this one, without a doubt, if we were to graph it, would definitely be a continuous graph. And so our domain and range will reflect that instead of listing out individual points or numbers like we did in example number 22. This is going to be similar to number 23, in which case we're going to have to use intervals to describe the domain and range. So I think the domain, how many hours could it have been? Well, any number of hours greater than or equal to 0. And how high were they? Any height greater than or equal to whatever they started at, 2,000. All right, this one's going to be a bit of a doozy. In 1990, the United States gross domestic product, called GDP, the total value of all goods and services made in the United States in 1990 was $5.7 trillion. Yowza! In 2002, it had grown to 12.9 trillion. And we're going to make a big assumption here. We're going to assume that the gross domestic product grows at a constant rate. And if it grows at a constant rate, that kind of means that, well, if you were to think about it in your head, it means it grows kind of like a line. And so we're going to use a linear equation to model this situation. Okay, so here we go. First things first, if we're going to create an equation, we got to go ahead and define some variables. So our independent variable, let's call that, well, you can call it one of two things. You can call it the year, or maybe I might suggest the number of years since 1990. I'm going to define it to be the year, but you may choose, or maybe you chose, to do something differently. And I'm just going to give it the unoriginal variable name x. And the dependent variable will be the United States GDP, and I'm going to say in trillions of dollars. God, trillions of dollars. How nice would that be? Okay, awesome. All right, so now from this information, we can get two data points. In 1990, the GDP was $5.7 trillion. So I'm going to create the data point in 1990 when our independent variable was 1990. Our dependent variable was 5.7. That's pretty cool. All right, I'll take it. In 2002, the GDP was 12.9 trillion. So when our independent variable was 2002, our dependent variable was 12.9. So now that we have these two data points, we can determine the rate at which the population is growing. We can kind of find out, how steep this line is. Its slope. The slope is a rate of change. How fast is the United States GDP growing? So, just to help myself out, I like to do a little labeling here. I might call this x1, comma y1, and I'm going to call this second one x2, comma y2, and that might help me remember how to find the slope. So the slope, or the rate of change in this case, let's see, so y2, 12.9, the final GDP minus the initial GDP over the final year minus the initial year. So we find in our numerator, we're going to find how much GDP increased, and I think it increased by, $7.2 trillion over a period of 12 years. And if we reduce this, we get 0.6, I believe, which means that every year the United States GDP increased by $6 trillion on average. That's pretty good. And so now that we have the slope, and I'm going to use this point right here, we can create an equation to describe the relationship. And I'm going to put it in two ways. The first way I like to do it is just kind of point-slope fashion, in which case we'll just have y minus 5.7 equals 0.6 times the quantity of, totally didn't leave myself enough room. Whoop. 0.6 times the quantity of x minus 1990, which is all groovy. I like something very similar to that, but not quite the same. Y equals 5.7 plus 0.6 times the quantity of x minus 1990. All I did was that equation right here. I just added the 5.7 over to the other side. And so this equation right here tells us, okay, excuse me, The GDP was 5.7 trillion in the year 1990, and it increased by 0.6 trillion every year after that. Oh, well, I just told you what the slope meant. That slope of 0.6 means that every 1 year, the gross domestic product went up by $0.6 trillion. So now we have an equation right here, which I'm going to copy and paste elsewhere as well, to describe that relationship, that growth. So if we want to predict the US GDP in the year 2030, all we need to do is take this 2030, slap it on in there, and let's see what happens. We end up with y equals 5.7 plus 0.6 times, well, 2030 minus 1990 is 40, right? It's basically saying, listen, 40 years later, if we grow at $0.6 trillion for 40 years, what are we going to end up with? And I think that 0.6 times 40 is 24. Certainly hope so. And so I think we predict that if we continued at this rate, we would find that in the year 2030, the US GDP would be $29.7 trillion. Now, granted, I just wrote y equals 29.7, but if I were you in a quiz exam situation, I would write this little blurb that in the year 2030, we predict the GDP to be $29.7 trillion. Equivalently, we could answer a different question. We could say, well, when do we expect the GDP to reach a certain number? Namely, excuse me again, $20 trillion. And all we need to do is, I'm just going to circle that 20, and we just got to plop that in here for our variable, which represents the GDP in trillions. So we end up with 20 equals 5.7 plus 0.6 rather, times the quantity of x minus 1990. All right, so this might get a little sloppy, but hey, I would let you use a calculator for this. So let's see, I'm going to subtract 5.7 from both sides. We end up with 14.3 equals 0.6 times the quantity of x minus 1990. And this is going to be the kind of nasty part. Let's go ahead and divide both sides by 0.6. Ugh. All right, I got to break out a calculator for this one, so bear with me. All right, 14.3 times, 14.3 divided by 0.6, 23.8333333. I'm going to call that around 23.8. So 23.8, I'm going to say is approximately, because we did some rounding there, equal to x minus 1990. If I add 1990 to both sides, we find 2013.8 is approximately equal to x. And so what I would say in an exam quiz situation is, listen, that means that sometime during the year 2013 is where we'd expect the GDP to reach 20 trillion. Maybe Halloween, maybe like Thanksgiving time, I don't know, late 2013.